couple of the high points are the fact that the machine was launched on relatively short lead time, was assembled within the tunnel. So at this point, we're doing a bypass tunnel around the machine that's been stuck. It's been decided, obviously, it's pretty dangerous conditions. So a bypass tunnel was approved, and the machine was ultimately assembled within a chamber within the tunnel. Here you can see a number of the characteristics or features that were put on the machine in order to excavate through this difficult geology. Instead of a double shield machine, it was a single shield machine. A lot of these features we're going to go through in a little bit more detail moving forward. It is worth noting that the screw conveyor during the initial design phases, where it was at the center of the machine, similar to a belt where the belt conveyor would be on a traditional machine. However, due to difficulty cleaning out the cutter head, something in these fault zones the contractor had good experience with at this point, or a lot of experience with at this point, it was requested that we move the screw down to the bottom, though the cutter head was still very much a rock-style cutter head. So as we look at all the features that were installed on the machine, the changes where the geology is better understood for the project, and a more appropriate machine has been selected. You can see some of the advance rates throughout the project up to this point. It's not going to set any world records, though there are, beyond machine performance, there are a lot of logistical challenges. For instance, there's still about 500 liters per second of water flowing out of the tunnel. This creates logistical challenges. But what I want to highlight here is you can see the gray bars. Those represent fault zones or where high pressure was encountered, in some cases exceeding 20 bar. And in most cases, there's a hit on performance. The performance goes down on the machine, but ultimately the machine is able to maintain a decent advance rate or some advance rate to get through those fault zones, get into better ground, and ultimately make better progress throughout the project. So that brings us to our first poll question. What resources are you most likely to consult when faced with a project in high cover conditions? International guidelines, technical papers, and case studies, manufacturer's recommendations, or recommendations, experiences from people I know.
And Brad, we have another question from the audience. In the event that tough conditions like rock bursting and squeezing ground occur, how do you decide whether to stop the TBM or continue?
Well, to give a slightly jaded answer, or maybe not jaded, I think it really depends on, first of all, how the contract is written, how those conditions are addressed in the contract, how it's going to be paid for. That being said, many contractors ultimately want to make a tunnel, so they're going to find ways and means to make that tunnel. The Grady project is a good example where they got a machine stuck in a fault zone. They went to create a bypass tunnel. The Almost project ran into many difficulties, some machine damage due to rock bursting. Ultimately, they, working with us and our field service personnel, fixed the machine and kept the machine, developed processes, made changes to the machine to keep the tunnel moving forward. And it looks like we have our results in, and most people look to be going with either people you don't know, and if you know manufacturers, what they recommend. I'm trying to move on to there we go. So we talked a little bit about the conditions that we see on projects. What are we recommending? The comparison between TBM types is a pretty involved topic. There are some people that aren't as experienced with them, so I'm just going to throw this slide up here. It gives a general overview of where you would expect to see these different machines. but again, this ultimately becomes a pretty involved topic. All those machine types, we're going to go through several different options that are available. Some are more applicable to others, one machine type versus another, but they're all very useful in understanding how we're going to address this ground. The first one we're going to look at is something that Cindra touched on earlier, and that's the ability to overbore. What we're trying to do, and this is to address converging ground conditions, what we're trying to do here is keep the ground from coming in or converging on the machine itself. The machines, in order to be able to go through or push through the ground, usually are designed to have a little bit of clearance around them. Once that's brought in, geology comes in, it can have